Good morning, everybody, and thanks for allowing me to speak at the ACI Concrete Convention. So, as he said, I'm a PhD student. I'm Willy, a PhD student, working on the multi-objective optimization of a sustainable ternary mortar for 3D printing. I'm supervised by Jean-François Caron from the Navier Laboratory in France and Claudiane Ouellet-Plamondon from ETS Montreal. So I will first introduce my subject and talk about the global objective of this study. Then I'll speak about the materials and the methods used in this study, and that will lead me to speak about the global optimization process that I'm using. And I'll conclude with the results, a little bit of the discussion, and the conclusion. So as we all know, the cement production is responsible for up to 8% of global greenhouse gas emissions annually, and that's not even mentioning other categories of impact or the concrete impact as a whole. And in that regard, concrete 3D printing offers a way to increase productivity, but also to reduce manual labor. And especially in our study, it proposes a way to reduce the material consumption. As we see on these figures from the French company X3, the concrete 3D printing benefits from the absence of formwork and the structural and topological optimization it offers. However, if we consider 3D printing concrete materials in the literature, especially 1K systems, which correspond to unaccelerated concrete, as opposed to 2K 3D printing systems which include a secondary mixing with accelerating admixture in the print head. If we consider these materials in the literature, we can see that they have pretty high cement content. And indeed, due to the rheological constraints of pumpability, shape retention, and buildability, along with the non-linear behavior of cementitious materials with increasing number of parameters, such as the adding of admixtures and supplementary cementitious materials, due to these constraints, the materials have high cement content, which means they have a high carbon intensity. So the global objective of this study is to propose an automated, reproducible methodology for reducing the environmental impact of 3D printing materials. So in this study, we will apply the method to a mortar with very low cement content, and we will focus solely on the global warming potential. So we chose to apply the method to a limestone calcined clay cement-based mortar named LC3 because it has a greater cement substitution potential. As we can see on this figure from Anthony and Al, the B45 mixture, which corresponds to 45% cement replacement, performs better at 28 days in terms of compressive strength compared to a traditional 100% ordinary Portland cement-based concrete. And also, additionally, we want to demonstrate that the methodology is robust and relevant for a higher number of parameters, so for added supplementary cementitious materials. As such, the materials we use are cement general use with 8% silica fume. We use also calcined clay with 80% metakaolin. We use limestone filler and sand with a maximum particle size of 2.5 millimeters. And we use the polycarboxylate ether-based superplasticizer. In terms of methods, so the physical characteristics are covered with rheological tests detailed on the next slide. The printability is defined through a literature review and through actual large-scale 3D printing at ETS Montreal. For the life cycle assessment, we use the software Brightway 2, which is a Python package, along with its graphical interface activity browser. And we use the database Ecole 3.7 cutter. Finally, for the optimization, we use artificial neural networks and a non-dominated sorting genetic algorithm named NSGA2, which are also Python packages. So we optimize our material for a continuous mixing/pumping unit with attached to a 6-axis industrial robot and the printing head installed. For the printability, so we have a range of rheological tests that cover the 3D printing time frame. So first, we have the flowability, which is characterized by the flow table test at 2 minutes, and we set the threshold at 120% flow. For the shape retention, we use a miniature version of the slump of the Abraham's cone, and we use the slump test at 8 minutes after rinsing, and the criteria is set at approximately 65 millimeter slump. Finally, for the buildability, we use the direct shear test at 30 minutes and 60 minutes. And through a regression with the results of the sum test, we get a linear structuration rate named Additive. And we set this criteria at 3.5 pascals per second. Note that this is an arbitrary criteria. We just wanted an elevation of 0.5 meters at 30 minutes and 1 meter at 60 minutes, with a 2 meter contour length. For the life cycle assessment, we built our life cycle inventory with mixed processes and adapted processes based on the Ecole database. So particularly, we have the binder components, which are cement generally used with silica fume, calcined clay, and limestone filler. And we associate these constituents to the other components of the mortar, which are sand, water, and superplasticizer, in order to conduct a cradle-to-gate study. So we exclude the robotic system, the printing, the transportation phase, the use phase, and the end of life. So finally, for the global methodology, so it's the optimization process is based on the publication in Digital Discovery from Vasilis Sergis and Claudia Nouel-Plamondon. So it revolves around the collection of experimental data via an optimal design of experiments. So we have our rheological data collected, and this is for the training of artificial neural networks that predict the rheological properties of our materials, along which I include a parameterized LCA model. And so the predictions of rheological properties and this LCA calculation will be used for the ranking of non-dominated solutions in a genetic algorithm. So at each iteration, we evaluate the proposed solutions. And through the basic principles of a genetic algorithm, which are selection, crossover, and mutation, we get a uniformly distributed set of Pareto optimal solutions, which means we have a set of the best compromises between the objective functions. So the idea then is to select 3 of the solutions for validation and reproduction in the lab. And the idea is to iterate this process a number of times in order to get progressively better results in the experimental regions that we explore. So for the results, the results are based. So the design of experiment is based on a reference material that we found through trial and error, with the objective to lower the global warming potential of our LC3 mortar. So the reference material has these properties: so 120% flow, 67 millimeter slump, 3.6 pascals per second Additive, and a global warming potential of 251 kilograms of CO2 equivalent per cubic meter. So these properties are already considered printable. So the objective now is to lower the climate change score while maintaining the printability constraints in an automated and kind of easy way. So for preliminary results of global warming potential, this is important to note because it will orient the study and actually the results of the algorithm. We plotted the weight proportion of each mixed constituent against its respective climate change score proportion, and we can observe that in our model, although accounting for 7% and 6% respectively of the weight proportion, the cement GU and the calcined clay account for more than 53% and 34% of the total global warming potential. And the pretty high estimation of calcined clay can be attributed to the kaolin production, the kaolin calcination, and the calcined clay transportation. So now for the results of the optimization, the dotted lines represent the normalized objective for rheological properties. So for flow and attic, we want a point that is on or above the dotted line, and for slump, we want a point that is around the dotted line. And at the bottom, you have the global warming potential reduction compared to the reference material. So for the first iteration, we can see that the algorithm, the multi-objective algorithm, captures the mixed design trends, but the errors can be still substantial, especially for the slump test. For the second iteration, the algorithm explores unseen experimental regions with lower global warming potential. As we can see, can go up to 13% reduction, but the errors are still substantial. And for the third iteration, we can see that the algorithm proposes two mixtures that approximately satisfy the printability constraints with 7% and 6% reduction in global warming potential. And from these two mixtures, we selected the last one because it satisfies the printability constraints of the flowability constraint of 120% flow. So we have found a mixture that has a 6% global warming potential reduction. So we can see that this is an effective process for reducing the global warming potential of complex materials in as low as 9 additional mixtures. And if we go one step further and we expand the experimental region to explore even lower cement content regions, we can see that in only 2 additional iterations 4 and 5, we have the algorithm proposes a mix that satisfies the printability constraints and even has a better structuration rate than expected. And it again lowers the global warming potential of 10 kilograms CO2 equivalent per cubic meter. So if we have a little bit a few comments about these results. First, the algorithm, when not taking any compressive strength criteria, always tries to minimize the cement contents. And but we see that it has a little effect on the other rheological properties, especially structural build-up, which is interesting. Then the algorithm optimizes the calcined clay content. Indeed, this calcined clay has a pretty high impact, not as much as cement, but pretty high. Indeed, in the LCA model, we have a conservative modeling of calcined clay. We consider calcination in a rotary kiln with natural gas, an electricity mix from Saskatchewan, Canada, which is 85% fossil fuels, for the production of kaolin, and we have a transportation distance of almost 3,000 kilometers. So that makes an impact factor of 658 kilograms of CO2 equivalent per ton of calcined clay, which is a pretty high estimation compared to the literature. It is our model with our material. Also, to be noted, the reference material that we found through trial and error is already quite effective in reducing the global warming potential compared to the mixtures from the literature, because it already has less than 160 kilograms of cement per cubic meter of mortar. But the goal of the study was to find a way to reduce the global warming potential even more in an automated and straightforward way. So to be noted also, we restricted the bounds of the mixture parameters after an initial iteration because the neural networks had too much trouble predicting too far from the design of experiment region. But now that the predictions are better in a lower cement content region, the parameter boundaries can be expanded as it was done for iterations 4 and 5. But overall, we can see that for a 6-parameter optimization with 4 to 6 objective functions, we can expect a substantial error, especially considering the dataset size of the design of experiments. We can we can expect a substantial error in the first iterations, but we can see in this study that with this methodology, the results get progressively better, the predictions get progressively better along the iterations. Now to conclude, this methodology is an effective way for reducing the workload necessary for material optimization, especially for complex cementitious materials. And it's an effective way to include the global warming potential in the mixed design process, which is pretty rare in the literature. It's reproducible with locally sourced materials and customizable objectives. So let's say we want to optimize another material which is adapted for 2K 3D printing systems, so with accelerated concrete. We could use other objective functions such as maybe another kind of flowability test or a reactivity with accelerating admixture test. Finally, it's possible to include the compressive strength back in the objective functions in order to switch objective. So the next step will be to identify a 40 MPa 3D printing mortar with a minimized climate change score in the experimental region that we define. So here are the references of the presentation, and thanks for your attention. I will be taking questions if you have any.
Great project. Looking at small question, the flow table.
Yep.
Do you do any drops?
Yeah, I do 25 drops in.
Okay, good. Then about your
yeah.
So your system and acceleration. I know you have that. It is. When people think in the past, right? You want to build out the work specifically, so you already said it's not there. People have to slow down the system speed, or just the layers, the next day, then the issue.
So, compared to traditional, just OPC-based mortars and concrete, LC3 has a better structuration rate. As we can see in the study, it goes up to 4 and 5 pascals per second, compared to traditional materials that have less than 1 pascals per second. And so the structuration rate after 6 minutes in this study we don't look at. but we can assume that it goes up in this trend until one day in the dormant period. I don't know if yeah.
One day 10 of material. So that is able to hold, material you go in the CC, like the
Okay, no, I haven't looked at this. I'm optimizing this material for prefabricated, just not very large scale structures. I'm just looking at the. No, not at all.
I have one question.
Yeah.
So, in your optimization, using for the direct
The cement?
Yeah.
Oh, I'm using cement, but I'm replacing, I'm substituting the cement in the binder with calcined clay and limestone filler.
Okay.
This is the principle of the LC3. Yeah.
Yeah, but so when you're showing the lower numbers,
Yeah, so I'm not trying actively to reduce the cement content. I'm just letting the algorithm decide which parameters are better for reducing the global warming potential while also maintaining printability constraints. So the algorithm told me that the minimization of cement content is best for this study, and I end up with a cement substitution in the binder that is more than 80%. Yeah, of course. This is a multi-material optimization, so you can use it with even geopolymer mixes or every kind of material, even for traditional concrete or traditional conventional construction.